Hey kids, welcome to section 5.4, graphing square root functions. Today you're going to learn how to graph a square root function and how to analyze a square root function. So the first thing we need to do is talk about the major characteristics of a square root function. So the parent function f of x equals square root x. Notice that it is a half of a parabola. The domain is from 0 to positive infinity. So basically, it's starting wherever the origin is of the graph. The range is from 0 to positive infinity. It's just the top part. The intercept or root is x equals 0. There is no symmetry. It is not defined for less than 0. That's because you cannot square root negative numbers. Notice the end behavior here looks a little different. The second end behavior is normal. As x approaches positive infinity, f of x approaches positive infinity. But look at the left-hand side. Notice that it's not as x approaches negative infinity, but this time it's as x approaches 0. That's because it's not going past that point at all. And so we're always going to be looking for, I call it the starting point. We're always going to look where that starting point is to see what the end behavior is. And then notice the extrema is going to happen at that starting point. So first thing we're going to talk about is domain and range. Identify the domain and range of each function. So if I were to look at f of x equals square root x minus 3, the domain is everything that makes the function able to get an answer when you plug in a value for x. So the domain is all the x's and the range is all the y's. Now I can plug in almost all of the x values in the world, but I can't plug in anything that's going to make the stuff underneath the radical be equal to be less than 0. So I need to figure out what makes it equal to 0, and then I can go from there. So if I were to set the stuff underneath the radical equal to 0, I would get x equals 3. That tells me that all the numbers from 3 and above are going to be able to be substituted in. So I'm going to do a hard bracket from 3 to infinity. Now the range, if I graph this, is just going to start from that starting point of 0 and be above it because it is a positive square root. So therefore my range is going to be from 0 to infinity. I'm never going to be able to get a negative value when I square root something because the square root of a number is always positive. And so therefore it's only going from 0 and above. If we look at letter B, our domain is going to be all the x values that I can substitute in. So if I take this x plus 6 and set it equal to 0, I'm going to get x equals negative 6. That's the start of my domain. So from negative 6 to infinity with a hard bracket at negative 6 and a soft bracket at infinity. Now my range is going to be connected to that plus 2. The plus 2 means I'm going to move the entire function up 2 spots, and therefore my range is going to go from 2 to infinity. Remember all that stuff we talked about translations in earlier chapters? That stuff is all still involved. So this plus 6 means I'm going left 6, and this plus 2 means I'm going up 2. That's where you get your values for domain and range. If we look at letter C, f of x equals the square root of 2x minus 3 plus 7. My domain is going to be whatever makes the stuff underneath my radical equal to 0. So if I do 2x minus 3 equals 0, I solve for x. I get x equals 3 halves. So I'm going from 3 halves to infinity. My range is going to be connected to this plus 7. That means 7 units up. So I'm going to go from 7 to infinity. If we look at letter D, my domain, I'm going to set 4x minus 8 equal to 0 and solve. So that gives me 4x equals 8. That gives me x equals 2. So my domain is everything from 2 to infinity. My range is connected to my translation down, which is negative 5. So my range is from negative 5 to infinity, including negative 5. Now, sometimes my domain and range might look slightly different, and we'll see that as we start doing problems. So remember, I talked about those transformations. Let's take a look at how it looks in a radical function. So if I have a horizontal translation, that's going to be coming off of this h. We've already said that we're going to the right if h is positive. We're going to the left if h is negative. Also, keep in mind, we learned in the past that if it looks like a minus h, we're going to the right. If it looks like a plus h, we're going to the left. Notice that the domain is connected to my h value. Then my vertical translations are going to be connected to my k value. If my k is positive, then my whole function goes up. If my k is negative, then my whole function goes down. Notice that in addition to the k value telling me my range, it also helps me to see that if it's greater than that number or less than that number. And that depends on the a value that's in front. So remember that a value in front also is connected to if it's reflected or not across the x or y axis. And so if the a value is negative, then my range is going to be everything up until that k value. If my a value is positive, then my range is going to be everything after the k value. And we're going to see that in coming examples. Remember that a value tells you about your orientation and your shape. And so if my a is less than 0, my graph is reflected over the x-axis. And then the a value can also tell you if it's stretched vertically or compressed vertically, whether it's greater than 1 or between 0 and 1. So let's see how to graph some of these functions. So in letter A, we have f of x equals 2 times the square root of x plus 3 minus 1. We need to state the domain, range, and end behavior. So the domain, remember, is connected to what's underneath the radical. So if I set x plus 3 equal to 0, I'm going to get negative 3, and that's why the domain is from negative 3 to infinity. My range is connected to my k value, which is a negative 1. So that means the whole entire function is translated down a unit. And so my range is from negative 1 to infinity. Another thing you can do is you can make a table of values to graph. Now, the first value that you should use in your table is whatever the starting point of h and k is. And so in this particular problem, your h and k is negative 3 and negative 1. That's your first order pair. Then you should go up in x value numbers and say substitute in negative 2. So if I substitute in negative 2 for x, negative 2 plus 3 is 1, the square root is 1, times 2 is 2, minus 1 is 1. So now I have negative 3, negative 1, and I have negative 2, positive 1. Now, if I were to substitute in negative 1 as my next value, I'd have negative 1 plus 3, which is 2. And the square root of 2 is a decimal. So let's not plug in negative 1. What if I plug in 0? Well, 0 plus 3 is 3, and the square root of 3 is a decimal. All right, let's not plug in 0. What if I plug in 1? 1 plus 3 is 4. Ooh, the square root of 4 is 2, times the 2 in front is 4, minus the 1 gives me 3. That is a much better example. Now the next one that you're going to be able to square root, we square rooted 0, we square rooted 1, we square rooted 4. Ooh, the next number to square root nicely is 9. Well, if I want the stuff underneath the radical to be 9, then my x value can be 6. 6 plus 3 is 9. Square root of 9 is 3. Times the 2 is 6. Minus the 1 is 5. And so 6, 5 is my last nice point. When you draw it, you start at the starting point, the h and the k, and then you graph it and pretend like you're doing half a parabola. Notice that my domain is from negative 3 to positive infinity, and my range is from negative 1 to positive infinity. Now I need to do end behavior. So as my x approaches positive infinity, what happens to my f of x? Well, my f of x is going to get bigger, so it approaches positive infinity. Now remember, the one on the other side is weird. So as my x approaches, now the farthest left my x can approach is -3. So as x approaches -3, f of x is going to approach -1. Notice that -3, -1 are the same numbers as h and k. So your end behavior, one of your end behaviors is going to match directly to whatever your h and k is. Okay, if I look at letter B, f of x equals -square root x minus 5. Well, I can make a table. Remember, my h and k is where I start. My h is going to be 5, and my k is going to be 0 because there's no number here. So I'm going to start at 5, 0. Then I want to plug in 6 because 6 minus 5 is 1. The square root is 1. Attach a negative, you get 6, -1. Ooh, look what happens this time. Notice it's going down, and that's because of this negative here. That negative tells me that it's going to open down. Then if I plug in 7, 7 minus 5 is 2. If I plug in 8, 8 minus 5 is 3. If I plug in 9, 9 minus 5 is 4. The square root of that is 2. Attach a negative, you get -2. 9, -2. There's going to be my radical function graphed. The domain is attached to the h value. Notice that it's from 5 to infinity, including 5. My range this time is different. Notice now that my range is 0 and below. So 0 and below means you have to start with the smaller number, which is -infinity, and end with the bigger number, which is 0. Again, directly correlated to h and k. Then my end behavior, as x approaches positive infinity, my f of x looks like it's going down, so it's approaching -infinity. On the other side, as my x approaches, well, my x can only go as far as 5. My f of x is going to approach 0. All right, let's see some more examples. Letter C, 1/2 times the square root of x minus 3 minus 1. Well, my h and k, my starting point, is positive 3, -1. So when I make my table, 3, -1 is my starting point. Then I want to substitute in 4. 4 minus 3 is 1. Square root is 1. Times 1/2 is 1/2. 1/2 minus 1 is -1/2, or -0.5. So 4, -1/2. If I plug in 5, 5 minus 3 is 2. Don't want that. If I plug in 6, 6 minus 3 is 3. Don't want that. If I plug in 7, 7 minus 3 is 4. The square root is 2. Times 1/2 is 1. Minus 1 is 0. So 7, 2. No, 7, 0. After that, it's going to get kind of tricky and ugly with decimals, so I'm just going to keep my graph like this. My domain is all my x values. Those start at 3 and continue on to infinity. So 3 with a square bracket to infinity with a parenthesis. My range is starting at -1 and getting bigger. So -1 with a square bracket to infinity. Again, h and k, 3 and -1. My end behavior, as my x's get bigger or approach positive infinity, my f of x's are also approaching positive infinity. On the other side, as my x approaches 3, my f of x is approaching -1. Again, h and k. All right, if we take a look at letter D, f of x equals -square root x plus 3. Notice the plus 3 is not underneath the radical, so that's a translation up 3 units. Notice also that there's a negative in front, which means my graph is reflected on the x-axis. So my h and k, are going to be 0, 3. That's going to tell me where to start my table, 0, 3, also where to start my graph. Okay, if I plug in 1, square root of 1 is 1, attach a negative, so that's -1, plus 3 is 2, so 1, 2. It's going down, which is good because of that negative. If I plug in 2, I get a decimal. If I plug in 3, I get a decimal. If I plug in 4, the square root of 4 is 2, attach a negative to get -2, plus 3 gives you 1. If I plug in 5 or 6 or 7 or 8, I get nothing. But if I plug in 9, the square root of 9 is 3. Attach a negative to get -3. Plus 3 is 0, 9, 0. Oh, my bad. Now, you can plug in numbers and get decimals, but why drag your calculator into it when you can just pick nice numbers that can square root easily? So my domain is all my x's, which start at 0 and go to positive infinity. My range starts at 3 and gets smaller. So that means I need to start with negative infinity, and it goes to 3 with a square bracket. My end behavior as x approaches positive infinity, what's happening to my y's? Well, my y's are getting smaller, so that's negative infinity. And on the other side, as my x approaches 0, my f of x is approaching 3. All right, let's look at some word problems. The speed that a tsunami or tidal wave can travel is modeled by the equation v equals 365 square root d. All right, let's just write that. 365 square root d. It says v is the speed in kilometers per hour, and d is the average depth of the water in kilometers. A tsunami in the ocean is found to be traveling at 145 kilometers per hour. What is the average depth of the water rounded to the nearest hundredth of a kilometer? Okay, so 145 kilometers per hour is a speed. In this problem, v is the speed. So I'm going to put 145 in for v. And the question is asking me what is the average depth, and d is the average depth. So I want d to be the variable in the problem. Okay, so now I got to solve for d. Well, in order to solve for d, I first have to get rid of this 365. If I do 145 divided by 365 on my calculator, I get a really ugly decimal, so I'm just going to put down the first few decimal spots. And now I got to get this d out of the square root, so the only way to get rid of a square root is to square. Now that gives me d on the right side. And if I leave the number that's on my calculator and square it without typing it or anything, it says nearest hundredth. So that's going to give me 0.63, and the units are kilometers. So if the tsunami is going 145 kilometers per hour, then the depth of the water is 0.63 kilometers. Okay, let's take a look at another word problem. The approximate time t in seconds it takes an object to fall a distance of d feet is given by t equals the square root of d over 16. Suppose a parachutist falls 11 seconds before the parachute opens. How far does the parachutist fall during this time? Well, 11 seconds is a time. T is a time. So I'm going to put 11 in for t. Now, in order to get into the square root function, to get to the letter, I need to square both sides. So 11 squared is 121. And I'm left with d over 16 on the right. To solve for d, I'm going to multiply both sides by 16. So that gives me d equals, it says to round to the, it comes out evenly at 1,936 feet. So if a parachutist falls for 11 seconds, then they fall for a little over 1,900 feet. All right, kids, that's the end of section 5.4. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.